Good morning, and thanks for the opportunity. Our goal is to digitize the Graham pollen collection. This is the most complete collection of tropical pollen in the world, the product of more than 50 years of work. This collection was mostly built by the late Professor Ala Graham while at Kent University. He donated it to us a few years ago. This collection is unique and a major asset of our institution. All the boxes you see in the photo contains microscopic slides. The collection has 25,000 microscopic slides that contain the pollen of 20,000 species of plants from the neotropics. Each slide looks very similar to the one you see in the photo. In the center, it holds the pollen that was extracted from an anther, and on the side there is a label with the name of the taxa and a number that is linked to an index card. These cards contain all the information associated to the pollen slides, such as the taxa name, the family, the herbarium where it was collected from, and how was it processed, among many other information. Before the pandemic, and thanks to the Smithsonian Transcription Center and its hundreds of volunteers, we transcribe all 25,000 index cards. We are in the process of adding a QR code to each slide that is linked to the digital information that was transcribed. The next step is digitizing each slide. Of course, the most difficult task. To do this, we are using 4 microscopes. 3 of them are light microscopes with a stage controlled by a computer, 1 size and 2 Nikon, with a 500 nanomicron resolution. One of the Nikon was sponsored by the Smithsonian Women's Committee, and we are very grateful to them. There is a new generation of confocal microscopy that is marvelous. The size LSM 980 with area scan that increased the resolution to 120 nanomicrons, thus providing details of the pollen grain that cannot be observed with bright field microscopy. This microscope is already in Panama, and by the end of April, it will be operating. But you may be asking yourself, what do I mean by digitizing the slide? Well, we are going to photograph 50 grains per slide with a numerical aperture of 1.34, a 63 plus objective, and 63 different focal planes per grain. This process is being done with bright light, DIC, also called differential interference contrast, and the confocal microscope. As you can imagine, the process will produce many files. I calculate that by the end of the digitalization, we will have about 78 million individual files that will occupy around 17 terabytes. How are we going to manage and see all those files? To do it, we have chosen a software called Homero that stands for Open Microscopy Environment. This is an open source, free software developed in Europe and used across many institutions in the world. With Homero, we can view, organize, and analyze this type of microscope images across several operating systems and only with the use of a browser. This is how an image in Homero looks like. We can move across the different focal planes just like you would do under the microscope. And you can add nodes or region of interest, measure features, and share the image or node with somebody else. I calculate that it will take about 2 years and 11 microscopists on a full-time basis to complete the digitalization. The image will become public as we digitize them. Why we want to do it? Well, there are three main reasons. First, we want the collections to be used. Right now, you need to travel to Panama to see the slides. And even if you are in Panama, checking 20,000 slides is just an impossible task. Second, the collection was mounted using glycerin jelly, and its lifespan is around 4 decades. Slides are decaying at a fast rate, so we need to digitize it as soon as possible. And third, these images will be used to build a training set for a neural network to help with the identification process. We published a paper last year showing that artificial intelligence can be used to identify pollen, but all depends on having a proper training set. At the Smithsonian has the best training set in the world for the pollen of the neotropics. Palynological studies has been done since 1916, and since then until today we have not changed very much in how we collected the basic data. A palynologist sits in front of a microscope for hours to count and identify pollen. I think, however, that our digitalization will move our discipline into a new era, the digital palynology, where most of the analysis will be done in a computer, opening the window to many different analyses that could not be done before. It's really a very exciting time to be a palynologist. I anticipate that these images will be used by a wide variety of users across multiple fields, including paleontological studies to assess paleovegetation and paleoclimate, in biostratigraphy to help finding oil, gas, and water, in archaeology, forensics, pollination studies, honey production, and even to assess allergies. And imagine an entomologist collecting the pollen in the body of a bee and then taking photos of the pollen that are uploaded on a website that is linked to our neural network, thus providing a preliminary identification of the plants that the bee visited. I see three major challenges that we hope to solve along the way. First, developing the best possible pipeline, as every item in the process needs to be repeated 25,000 times. Second, developing a proper data support to handle the images, and that's still a major weakness in Stride. And lastly, it's long-term storage. Pollen grains are beautiful, and hopefully we will be able to share the beauty with the world very soon. Thanks a lot for your time.
Good morning. Thank you very much for listening to our presentation, and I'm glad we. So, if you have any question, please let me know. The first question that I got is how the COVID has affected our project. Well, it really has affected us in a number of ways, but the most important one that is still having an effect on the project is logistics, because we did not have any of the microscopes that we are using or are planning to use for the digitalization. And it has taken many, many months for the microscopes to arrive, especially because a large part of the microscope have digital components. And so you may have the whole microscope ready to ship, but there is a chip that is lacking in a particular component of the microscope. So we are still waiting for a microscope to arrive. It's supposed to be in a cargo ship that is going from Miami to Panama in the next few weeks. We have another microscope, the confocal, that is in our basement, and the people from Germany in size are coming here at the end of April to put it back, to put it together. And really, so far, we have just one functional microscope. So it's taking several months for every step to move ahead. And it's something we cannot control because this is a worldwide logistic problem. But I hope as COVID improve a little bit, we can move faster. But it still is a major challenge. Another question that I have is the IT infrastructure we have here in Stride. That's something that is still a major step that we need to solve. Even to the point that the internet that we have here in Panama, at least in Stride, is still too slow, about 70 megabytes per second. And when you are dealing with several gigabyte files, moving them to a slow internet is something that is taking a long time. So that's something we need to solve in the next few months. Another question is, what kind of research do you think making these slides available will unlock? It will help in a variety of studies. So imagine somebody doing a phylogeny of plants and they want to incorporate pollen. Well, the pollen would be fully digitized and from the plants that we have here in the Graham collection. And you can take this pollen, you can use artificial intelligence to identify any unknown pollen, and you can build the pollen into the phylogenies that are being produced with DNA. And there are many other, I can think of many other uses, as I explained in the conference, related to paleontology and biostratigraphy, helping to assess the identification of unknown pollen grains in the fossil record and also out in the forest. How large are the file size of each image? How do you manage them? Well, every individual pollen grain has 64 digital planes, and the total size of a typical image is around 15 to 20 megabytes. But we have millions of them. So right now Stride just bought a new server with a 1,000 terabyte capacity that has not arrived to Panama, and that's the place where we're going to store the image for the next couple of years. But the long-term storage is something we still have not been able to solve, but we have to solve it at some point. Now, viewing the images will be using Homero, as I said in the presentation, because that's an open source and very reliable software that has been developed by the European nations, especially for medical applications. Right now, many oncology studies to assess cancer cells are being used using digital files. They do a biopsy, take a slide, and then digitize the slide, and all the counts of the bad cells are done using neural networks. And Homero was developed to help in this process because the doctors were facing with the same problems we are facing now. You have big files and they're very hard to manage in your computer, so you need a server that can handle the volume of each image and you can actually work with them. Do you have plans underway now to develop neural nets for pollen identification? Yes, we published a paper in PNAS last year or I think 2 years ago, where we developed the pipeline needed to analyze the identification of pollen using neural networks. And the system worked very well. We want to take the same process we already developed for a particular plant family to the whole set of families in the neotropics. And thanks to the Graham collections, because to do that, you need a good training set. And building a collection like the Graham will take another 40 years. But thanks to Alan Graham, we have the collection here at the Smithsonian. How is going to be the public interface with these, all the images we are going to produce? That's something we still have not solved. How the people out there actually are going to be able to grab the image and use it for their own studies. And that's something we also need to solve in the next couple of years. This digitalization has never been attempted before for palynology. So many of the steps we are taking are really unknown. We are just developing the step as we go along. So there are many ways, many things I still don't know how are going to be solved, but I know that we'll solve them along the way. Will you incorporate digitalization into the workflow for newly collected samples? Yes. We know that the digitalization will allow to have a permanent record of the palynological slide. So now even we are doing the digitalization for both the fossil and living and extant pollen. So we can have a permanent record. And also because the files can be shared, you can as several scientists can access the information in the same slide at the same time. And before you have to actually ship the slide to another scientist for that to put in the microscope and see what you have seen before. How's the accuracy of ID by artificial intelligence? In the study we already did, the accuracy was really good. It was as good as a human palynologist. And I have been doing palynology all my life, almost 30 years of work. And I have counted millions and millions of pollen grains. And I'm glad this technology is helping us to remove counting the most common taxa out of the equation. And we can focus more on the rare taxa that no system of artificial intelligence will be able to help us with. So I'm very happy that we are moving into this direction. And I see a lot of potential across many different fields. But the key factor is the training set. That's the most difficult part, and that's where the Smithsonian can make the difference because we have the best collection of neotropical pollen in the world. Will this image become part of the open access collection at the Smithsonian? Yes, of course. We plan for the image to become public as we digitize them. And everything we do here will become public. That's the main goal of this project. It is possible to find a new taxon by identification by AI. Well, the AI analysis gives you the probability of an unknown taxa to belong to the training, to any of the taxa in the training set. So if you don't find a match, if the neural network doesn't find a match, or find that the probability of your unknown taxa to belong to any of the taxa in the training set, it will mean that either you don't have that taxa in your training set, or it's a new taxa. Are there other institutions with similar pollen collections? If so, do you have plans to partner with them monomero. For the neotropics, we have the best collection by far. But I know that the Kew Botanical Garden has an excellent collection of pollen, especially from Africa and Asia. And I'm sure once they see the first result of our collection, they will join us and they will follow the same protocols we are developing here, because they are facing the same problem we have, that the collections are not used to the full potential, because you have to go to London to put the slide in the microscope, and the slides are also decaying, and this pipeline, I think, will allow many collections across the world to digitize their own. Will you be willing to share your neural net training set once it is refined? Yes, of course. The whole training set will be available for the public, especially because every month there is a new, a better algorithm to do neural network. And so in our own benefit, is much better if the public has the training set and do extra analysis with them. Now the pipeline, the most difficult part of the bottleneck is doing the digitalization of the collection. That's what we want to focus, we'll be focusing in the next 2 years. How is this project being funded? Well, the collection, the Microscope themselves, the funding has come from a variety of sources, from public, from private donors to the Smithsonian itself. Yeah. And we continue working with private donors to make this happen. There are a lot of research right now in artificial intelligence, in neural networks, to try to understand why the algorithm works in the way it works. So you get a match, but you don't understand very well why this particular algorithm gave you the match. And so there is active research trying to understand this black box that are the neural networks. And there is researchers that we partnered with in Illinois, Suranji Punyasena, that is making huge steps in understanding the algorithm themselves, to the point that we'll be able to use details of the morphology of the pollen into phylogenies derived from the neural networks themselves. Well, thank you very much for your time, and I hope you continue seeing all the different projects that are happening at the Smithsonian. Thank you very much, and goodbye from the warm Panama City.